Hello and welcome back to this latest video, and on this video we're going to be talking about logic gates. There's different types of gate. The commonly used gates are AND, OR, NAND, NOR, exclusive OR, and we'll just basically go over these different gates, what we call logic gates, and explain how they work. And later on in the video I'll get some chips, some integrated circuits out my junk box here, and we'll pick a few out. These are all logic gates, TTL and CMOS logic gates, basically integrated circuits. We'll plug them into a proto board and we'll wire them up and we'll try some just to make sure that we get the results that we expect to see. But first of all, we'll talk about a little bit of theory behind how logic gates work. We'll start here. So okay, logic gates. If you haven't came across logic gates in the past, if this is something new to you, or maybe you've heard about them but you don't really know much about them, the best way to visualize logic gates is if you had batteries and bulbs in a circuit, either in a parallel circuit or in a series circuit with switches, that sort of thing. And it's nice to sort of visualize some of the gates in this way because it makes it quite tangible. You can really think how it works. You can see how they work. So probably the easiest logic gate out of them all is probably the OR gate. Okay, so, and the OR gate you could represent by two switches. Let's say there's a switch and there's a switch. Two switches. You could call that A and you could call that B. Alright, so nothing complicated, couple of switches. If you wire the two switches in parallel like that, and then you put all this in a circuit, like with the battery and a bulb. Okay, that's a lamp there, that's a battery, it could be a 9-volt battery, anything you like. Hopefully you can see, if you have switch A on, okay, so let's put that switch down now and put it in the through condition. No matter what state B's in, the bulb will light up. Or if you put switch B in closed and switch A open, the bulb still lights up. You've got a circuit. Very simple, very basic principle there. So you can see where the word OR comes from, because it's A will light the bulb or B will light the bulb. If you put both switches on, it still lights the bulb. So any combination of on of these switches will light the bulb. The only time the bulb won't light is when both switches are off. And that's a good representation of an OR gate. Very simple to visualize. Just think of it like switches in parallel. So what about another gate? Let's try another one. I'll see if I can fit another one in here. What about the AND gate? This is an AND gate. I'll separate these a bit. OR gate, AND gate. Now the AND gate, we can use our same switches but in a series configuration. So for an AND gate, you could have one switch there and another switch there. Put that with the battery and the bulb. Call that A, call that B. In this case, two switches, A and B. You can appreciate if only one of the switches is on, A, then the bulb won't light up because the circuit's broken by B. That's open, that's closed, no light. Again, very simple. Open this switch and close this switch, so now this one's connected through but this one's off, basically the opposite of what we had, and still the lamp won't light up. It's only when you get A and B both on, then the bulb lights up. That creates the circuit and the current can flow and the bulb can light up. So that's the AND gate. That's a good simple representation of an AND gate, whereas A and B are our input terminals and the lamp is the output terminal. Think of it that way. And just to recap on the OR gate, that's the other way around. So either A or B can be on to light the lamp. So that's an OR gate, that's an AND gate. Okay, so moving on, what about other gates? We've looked at the OR gate, we've looked at the AND gate. What about other gates? Well, another important gate, and we're going to need to know this one before we can look at the other ones, is an inverter. In a simple inverter, you have a signal where an on signal, or a 1, becomes 0, and a 0 becomes a 1. Input of a 1 would go to a 0 on the output. It's basically just the opposite. And 0 on the input would go to a 1 on the output. So whatever you put in is inverted. It's the complement, if you like, the opposite to the output. And that's an inverter gate. Very simple. And it has the actual electrical symbol like that. It just looks like a triangle. And you'll notice that there's a little circle on the end. You can see that there. Like a little ring on the output. This is the input and that's the output. And this is for our inverter. Whatever you put in is reversed to the output. Very simple. And you'll notice, as I said, it's got a little circle on the output. And that actually tells you that the signal is inverted. Whenever you see a logic gate, doesn't matter what type of gate it is that you're looking at, it will have a little ring on the output to show that the signal is inverted. If it doesn't have the ring, this would actually be what they call a buffer, where the signal would just be the same all the way through, and all it's really doing is doing a current transformation. It's working like an amplifier, really. Small signal currents to big currents, that sort of thing. But there wouldn't be any logic change. You know, a 1 in would still be a 1 out. But because we've got this little circle on the output, it means inverted. It's an inverter gate. Now, if we want to look at other gates, now that we know what this is all about, let's take our OR gate, where A or B can equal an output. But let's invert the output and turn this into a NOR gate. Okay, a NOR. Now with a NOR gate, the N stands for not or. Not or. And not means the reverse. It's inverted. Okay. Now if you were to look at the electrical symbol of a NOR gate, it basically looks like that. That's an OR gate. It has a curved front usually on the front of it. So it has a curved input. That would be an OR gate. Like what we're showing here, but we want a NOR gate. Now to invert it, or not OR it, if you're with me, hope you're following this, we need to do this and put the little circle on the output. That inverts the output. So that circle means invert whatever you would normally have had. It's an OR gate, but we've made it into a NOR gate by putting a little circle on the output. So if we go back to the original circuit for the OR, you'll see that switch A or switch B, either one of them can light the bulb. But we've just put a little circle on the end and we've just inverted that. Whenever the bulb's on, you make it off. Whenever the bulb's off, you put it on. If you can see, if both inputs are off, or open circuited switches, normally the bulb will be off, but we're inverting that so it'll be on. Okay, so that's our NOR gate, which is basically the OR gate with a not inverted circle on the output. So that means whatever an OR gate does, to the opposite of whatever the output would normally be. And we'll put that into what we'll call a truth table in a moment. In fact, we'll put all of these gates into a truth table, and then we can look at the actual logic states in terms of ones and noughts in a table, what we call a truth table, which describes how the gate is working. Onward on to the next one. How about a NAND gate? Here's another one. Now a NAND gate, you've probably guessed it from the NOR gate. The N means not and. So if you remember on our AND gate, we had the two switches in series. A and B had to be both on before you got an output. But with a NAND gate, it's the opposite of that. And the symbol for a NAND is like that, with a little bobble on the output. That's an AND gate, and it has a straight edge to the front to make it separate from an OR gate. That would be A, B, and that would be our C output if you like. So that's our NAND gate with our circuit diagram with a little circle on the output symbol. Now what we can do is describe the inputs and the output in terms of a truth table. So we can talk about truth tables to describe how the gate is actually functioning. And if we say, let's do a table A, B and C, where A and B are the two inputs and C is the output, we can describe the input like this. We can say, well, if both inputs are 0, now this is a NAND gate, so it's not an AND gate anymore, it's the opposite of an AND gate. So 0, 0 would actually equal a 1. Okay, does that make sense? So both inputs are off. An AND gate would be off because none of the inputs are, both inputs have to be on before you get an output. So if we just think of it as an AND gate first, what would that do? 0, 0 of the switches, of the inputs, the output would normally be a 0, but we're inverting that, as I've said before, so we actually get a 1. What about the next state? 0, 1. Well, that's also a 1. And 1, 0. Well, that's also a 1. What about 1, 1 when we put both inputs on? Now, if you think about an AND gate, both inputs are high or on. That would normally give you a 1. So invert that. That's a 0. So that is the truth table for the NAND gate. 0, 0 would give you a 1. 0, 1 would give you a 1. 1, 0 would give you a 1. 1, 1 would give you a 0. There is another gate worth talking about, which we see all the time in electronics, and that's the exclusive OR, or EXOR. And this is a bit of a strange one, but it's used a lot, and it has a lot of uses. It's not the same as an OR gate, whereas any of the inputs would give an output high. An EXOR works on difference of input. So only when there's a difference between the two input terminals, then you get an output of high. It's a bit like you can think of it like a difference indicator. If something's different, if the two inputs don't match, then you get a true output, you get a high output. First of all, let's look at the symbol for that. And the electrical symbol is like that, where it has a curved line in front of it. and then you have the curved gate shape itself coming out. That would be A input, B input, C output. So if we were to do a truth table for an exclusive OR, what would that look like? Well, let's have a go. So we've got inputs A and B and output C. So for 0, 0, well, they're the same. You know, a 0 equals 0. They're both the same. So the output would be 0. 0, 1, well, they're different. So the output is 1. And 1, 0, that's another 1 because they're different as well. And what about 1, 1? Both inputs high, both switches on. Well, they're the same. 1 equals 1. So the output is 0. So you can see that there's only when there's a difference of the inputs, these two conditions here, that we'll get a 1, a true output, if you like. We normally refer to a 1 as being a true or a high state, and a 0 as being a false or a low state. There's different terminologies, but they all mean the same thing. High or true or a 1, logic 1, it's all the same thing. That's the exclusive OR gate. If you like, think of it as a difference indicator. Okay, so just to recap with the gates that we've spoken about so far. So we're looking at 6 major building blocks really, which is the basis for nearly all logic circuits. Let's just recap. So we have the AND gate, where that's the symbol there with a straight front and a curved back. A and B, the inputs, C is the output. So you only get an output when both inputs are high or true or on. Everything else is 0. So it has to be A and B before output goes on. Then we have the OR gate. And with the OR gate, that's the symbol there with its curved input front. The AND gate was flat, if you remember. This one's different. To show it differently on a schematic diagram. This is the OR gate. A and B the inputs again. C is the output. Now with an OR gate, if any of the inputs are on, then you get a true 1 output. It's only when both off, then you get a 0 output. So A or B can be on. A or B can be on. A or B can be on. A or B, if you like, or both together, doesn't make any difference. On, that's the OR gate. Then we had the NAND gate, whereas with a NAND gate, that's the symbol there. Again, it's like a flat front, just like the AND gate, but it's got the little circle, which inverts the output. That's what the N's for. It stands for not and the circle means not, or complement. A, B, and C yet again. 2 inputs and an output. Now in this case, it's the output of whatever an AND gate would be. If you remember with an AND gate, it had to be both on to give a 1. So basically everything else would be off, so you invert it. So 0, 0 would be a 1, 0, 1 would be a 1, 1, 0 would be a 1, and 1, 1 would be a 0. Only when they're both on, the output goes to 0. The inversion of an AND gate, a not AND gate. So then we have the NOR gate, which uses the same principles as before, where we've got the little circle on the output, which means not OR. So whatever an OR gate would give us, we invert it because of the not symbol. So for A, B inputs and C output, this is what we would get. Normally for an OR gate, any of the inputs can be on, and that would normally give us a 1 output. So this is the inversion of that. So they're now all 0, and it's only when there's no input at all, you get a 1 output. Okay, it's the exact opposite output of what an OR gate would be, a NOR gate. Then we have the weird one. It's not really weird, it's actually very useful. The exclusive OR, or the EXOR, as it's sometimes reduced to. And that's the symbol here with its curved line on the input and a curved gate front end as well with the 2 input pins. That's the symbol. And the EXOR is basically a difference detector. 0, 0 would give you a 0 because they're the same. And 1, 1 would also give you a 0 because they're the same. So only when there's a difference, 0 and 1, well that's a difference, that gives you 1. And 1, 0, they're different, so that gives you a 1. So whenever there's a change of the input, when they're not equal, then you get a 1 output. So that's an exclusive OR. The most basic of gates is probably the inverter, where you've only got 1 input, you don't have a B anymore, and you've got the output pin, which I've just called C. And basically whatever you put in, it's the opposite. 0 in, you get a 1 out, 1 in, you get a 0 out. And it's this inverter functionality that we see on the output of NAND gates and NOR gates, where you have a circle on the output. That's basically what the inverter's doing. And that's really the truth tables for all the major gates. That's all the 6 major gates. Everything pretty much revolves around those. So If you know these truth tables for these gates, then you pretty much can do anything to do with logic. These are the building blocks that everything else is based on. The only other gate that I haven't talked about is a buffer, what I call a buffer, which is just, it's not an inverter, it's just a straight through. So a 0 would equal 0 and a 1 would equal 1. It's not really a logic function because it doesn't transform the input to the output or anything. It just simply passes straight through, and all it does is current amplification. So you can have, you know, a small signal coming in and a big signal coming out. It's called a buffer amplifier, if you like, or a buffer gate. Now, that's the theory of it all. We've looked at the symbols, the electrical symbols for the gates, and we've also looked at the truth tables of the gate functionality. And if you know those, well, you've pretty much got gates sorted. And there's lots of websites on the web where you can download these, and I can print them out if you want to study them in any further detail. But hopefully that gives you a grasp of how they work. So now let's actually try a few gates in practice, and we'll put some chips on a board and with some LEDs and that kind of thing, and see how they work. Here's a typical example. This is an integrated circuit, a chip, and this particular one it has NAND gates in it. It actually has 4 NAND gates in a single package, what we call a package or a chip. And this particular one is a 7400. It's called a 7400 device. That's a TTL. The full name is a quad 2-input NAND gate. In other words, quad, 4 of them, 2 input for each NAND gate. So you get 4 in 1 in one of these. You get lots of different types of gates, logic functions, and typically in these kind of packages, although these days a lot of them are surface mount, so they're even smaller, but these are quite common, and you see a lot of them in beginner circuits, that sort of thing. When you're starting out, you tend to use these, but you still see them in some commercially produced products as well. Less so now, nearly always surface mount now, but the functionality is quite similar. And as I say, that's got 4 2-input NAND gates, quad package, if you like, quad gates in the one package. That's a 7400, so let's put it into the protoboard and power it up and see what it does. And here we are with our first gate to try. Let me just explain what's going on here. We've got the chip in the board here, and this particular chip is a 7400 or 7400 quad 2-input NAND gate, and I'll show the pin out for that on the screen here, so you can look at the designation of all of the pins of that chip. Basically, it's got 4 NAND gates in it, both with 2 inputs each. And what I've done is supplied it with a 5-volt supply coming through these blue and orange cables here. So we're driving it with 5 volts from the power supply. Got a little LED here, which is actually a 5-volt LED. It has a little internal resistor, and that allows us to put 5 volts straight across the LED without destroying anything. So it's designed to work with logic levels directly, and that connects to the output of the gate of one of the 4. So there's actually 4 packages in here, 4 gates. I'm only using 1 for this experiment, and the LED is connected to the output of that first one. I've got 2 switches, little micro switch things, clicky switches, tactile switches as they call them, and they're connected to the 2 inputs of the gate, input A and input B. Now if you look at the truth table that we did earlier for the NAND gate, we've actually got this, which is the 2 inputs. That's our 2 little switches, and C is our LED, the output lamp. And what we should see is straight away is that for both switches off, we should get a 1 output. And we do actually see this condition straight away. So I'm not pressing any of the switches yet. These are both open. And we are indeed getting a 1 output, a high or a 1 output. That's correct. So 0, 0 in, we should get a 1. Now what if I put one of the switches on? Doesn't matter which one. Either put B on or put A on. It should remain at a 1 or illuminated. So let's try that. I'm going to press one of the switches here. That didn't do anything. Let's press the other switch. That doesn't do anything either. You'll have to take my word for it. I am clicking these. Don't know if you can hear that. That doesn't do anything. That doesn't do anything. And the LED remains on. What happens when they both go on? Both switches on. The LED should go off. Let's try that. And I need 2 hands for this. Press them both. LED goes off. Leave go of them. So either one of them doesn't do anything, and both off, like right now, doesn't do anything. LED stays on. Press them both. LED goes off. That's exactly right, and that checks with the truth table. Only when they're both on does the LED go off. And that's a 7400 NAND gate. Here's another chip. This one is a 2-input exclusive OR gate, and the chip number is a 7486. This has also got 4 gates in one package, 4 exclusive OR gates, both with 2 inputs each. So I'm only using one of the one of the package of 4 here for this test. And again, we've got our LED on the output, and we've got 2 switches here, just like before, on the 2 inputs A and B. So for the truth table, let's remind ourselves of the truth table. We've got 2 inputs, A, B, and output C. Okay, so we've got both switches are off, and there's no LED being lit, which is correct for the first line. If we press either of the switches, whether it's B, that switch on there, or whether it's A, but not both, then we should get an output of 1. So let's try pressing one of the switches, either A or B, it doesn't matter. We should get an illuminated 1 LED there. So let's try that. Let's try this one. Yep, that one comes on. Let's try the other one. Yep, that comes on. Now remember, we said if they both go on, we should get a 0, so it should not light on both of them. And I need 2 hands for this. Press them both. Now they're both pressed. If I release one of the switches, it comes on, both pressed. Release the other switch, so either one, which creates a difference, that's our difference indicator. Either one of them, but not both, that actually illuminates the output. And also if I release both, it's also off. So that's exactly correct. That's the exclusive OR doing what it's meant to do. Only when there's a difference, we get a 1 output. This is another chip. This one is the 7405, which is classed as a hex inverter. In other words, it's a package of inverters with 6 in one chip, called hex inverter. So there's 6 of them in one chip, and I've just got one of them connected, gate number 1, which is just the first one here on this set of pins here. So as you can see, with the switch not pressed, the LED is illuminated. That's correct, because this is now logic 0, not pressed, and we're getting a logic 1 out. If we press the switch, that gives us a 1, so the LED should go off. Let's try that. Yeah, so that's now pressed, and that's now released, pressed, released. So now our truth table, that's exactly correct. A 0 gives a 1, and a 1 gives a 0. Okay, so I hope you've enjoyed this brief overview of logic gates. We've shown you a couple of actual practical examples with using chips. TTL chips in our particular case, but they come in lots of different types of chip. TTL, CMOS chips, LS, HS, high-speed versions these days. Usually smaller than these in surface mount packages nowadays. And but they all pretty much do, you know, all these different gate functions using these truth tables. Inverter, which is the most basic of all, it's just 1 in, 1 out. NAND, AND, OR, NOR, and exclusive OR. Those are the main combinations of gates, and from the combination of all these you can produce some very complex logic circuits, things to do arithmetic calculation, plus minus times divide operations. You can use it for you can make logic circuits to work out all sorts, and it can get quite mathematical as well if you get into that side of things. Usually when you're repairing equipment, you normally come across a chip like this or a couple of chips which do a basic logic function. You see a lot of exclusive ORs, mathematical type computational circuits as well. So, but you see all these used in different purposes. Once you've got a good idea of how logic gates work, you know, you can really progress after this, and then you can start looking at things like microcontrollers, how they have many of these built in, many of these functions is all kind of in one chip, which you program using software. So if you want a particular function, like let's say an EXOR, you can program that into the chip using C or using C++ language. And indeed, in C and C++ languages, you see a lot of logic being used in the code itself to produce where that you can then program into a chip, and you can have many of all these all combined into one particular chip to do very complex functions indeed. And it's all software. You're not dealing with single gates in a chip anymore. This is a hardware version, if you like, whereas in a microcontroller you would be dealing with software versions of what that does, of these truth tables, if you like. That's getting more complicated, and we're not going to cover that in this video. That's probably for another subject, probably when we start talking about microcontrollers. So we're going to leave that there, but I hope it's given you a good overview of logic gates, truth tables for each of the main gates that we tend to come across in real life applications, and we've shown a little bit about what they look like in practical terms with an LED and switches and what have you, to give you a feel for what they do. So thanks very much for watching, and here's to the next time.